My name is John Albers, and I'm going to be talking about some work that I've been doing with Matt Newman that is focused on the predictability of the North Atlantic Oscillation on subseasonal timescales. In particular, Matt and I have been focused on two questions. One, can we predict when NAO forecasts will be skillful? That is, can we identify forecasts of opportunity ahead of time? And if we can we identify the physical processes that are responsible for these higher skill forecasts? To answer these questions, we are going to be primarily relying on what's called a linear inverse model, or LIM, which I will explain in the following few slides. In terms of NAO hindcasts, I will be showing forecasts from the LIM, and for comparison purposes, I will also be showing hindcasts from the ECMWF IFS model. To identify high-scale forecasts, I will be using the LIM signal-to-noise ratio, while identifying the physical processes responsible for the high-scale forecasts will be accomplished by considering an eigenmode decomposition of the LIM's forecast operator. In terms of the NAO, we will be considering it for winters between 1997 and 2016, where we compute forecast skill as the correlation between the predicted and observed NAO time series. So what exactly is a linear inverse model? Well, a LIM is an empirical model constructed from lagged covariances between observations of various atmospheric and oceanic variables. Here we include sea level pressure, geopotential height at 500 millibars, tropical heating and tropical sea surface temperatures, and both a tropospheric and stratospheric stream function. All of these variables here we've taken from the JRA 55 reanalysis. So the LIM is constructed by taking advantage of the timescale separation between two types of atmosphere-ocean processes. On the one hand, there are processes with decorrelation timescales of less than a week, for example, rapidly evolving individual weather systems. On the other hand, there are processes that evolve more slowly, for example, shifts in the jet stream that are associated with things like the NJO or ENSO or sudden stratospheric warmings. The slowly evolving component that we hope might be more predictable on subseasonal timescales are modeled by our forecast operator, L, here, which is constructed from 7-day running mean anomalies of our forecast state vector, X. The LIM approximates the rapidly decorrelating nonlinear remainder, that is, those individual weather systems and things like that, via state-independent but observationally constrained Gaussian white noise. All right, so we run the LIM in two ways for our results today. First, we run it as a forecast model, in which case we generate an ensemble mean forecast at every forecast lead tau for weeks 1 through 6. But we also run the LIM as a climate model, in which case we force it with observationally constrained white noise, and we run it out for 300,000 days. Now, as I mentioned at the start of the talk, we are interested in identifying periods when we expect NAO forecast skill to be particularly high. Now, in the LIM framework, this is relatively easy to do because the LIM partitions each forecast into an ensemble mean forecast signal. That's the part on the left there. That's the forecast operator L times the state vector, and the LIM noise forcing on the right, which represents the forecast uncertainty. So we use these two terms to calculate the LIM signal-to-noise ratio. That is, we identify forecasts that we expect will have high skill. This means that at every forecast time, we calculate a prediction of the forecast skill, and this is lead dependent. Right? So for a given forecast, we have a signal-to-noise ratio prediction, a skill prediction for weeks 1, 2, all the way out to week 6. So once we've calculated the signal-to-noise ratio, for all forecasts at every forecast lead, we take all of the forecasts and we put them into one of two bins. In the first bin, we take the 15% of forecasts that had the highest signal-to-noise ratio. That is, forecasts that we expect should have higher forecast skill. In the other bin, we put the remaining 85% of forecasts that we expect should have lower skill. For the high expected skill forecasts, we see that skill remains at or above 0.5 to 0.6 all the way out to forecast week 4. However, for the remaining 85% of low expected skill forecasts, we see that for both the IFS and for the LIM, forecast skill drops below 0.5 beyond forecast week 2. What is notable here is that the LIM's signal-to-noise ratio identifies high skill forecasts, not only for itself, but also for the IFS. So now that we've identified which forecasts are the high skill forecasts, the question remains, what are the physical processes that are responsible for these high skill forecasts? To answer this question, we conducted an eigendecomposition of the LIMS forecast operator. What I'm showing here are the corresponding eigenvalues from that decomposition. The vertical axis is the e-folding time in days of each of the eigenvalues, and on the horizontal axis is the frequency of each of these eigenvalues. Two distinct groupings of eigenmodes immediately pop out, and I've highlighted those in blue and in green. The first set of eigenmodes, which we are terming the stratosphere SST modes, have long e-folding times, longer than 32 days, and all have low frequencies. Within this set of eigenmodes is one group of modes that are associated with joint SST and stratospheric variability, and one purely stratospheric eigenmode that has no SST component. The remaining eigenmodes that we're terming the internal variability modes, highlighted in green, all have shorter e-folding times, less than 22 days, have a continuous range of frequency, have no SST component, and are dominated by tropospheric variability. And I should mention that within this second eigenmode internal variability subspace is an eigenmode that represents the MJO. Separating the LIMS eigenmodes in the manner I just outlined allows us to decompose any time series of LIMS state vector data, or more generally, any time series of data projected onto the LIMS state vector, into variance associated with internal variability eigenmodes versus variance associated with the stratosphere SST eigenmodes. What this therefore allows us to do is to rerun the LIM hindcast with filtered initial conditions. That is, we create one set of initial conditions where we zero out the variance associated with the internal variability eigenmodes, and a second set of initial conditions where we zero out the variance associated with the stratosphere SST eigenmodes. This in turn allows us to isolate how the two types of eigenmodes each contribute to NAO forecast skill. So what happens if we rerun the LIM hindcasts, but we only include in the initial conditions variability that's associated with either the internal variability eigenmodes of the LIM or the stratosphere SST eigenmodes of the LIM? For reference, I'm showing the black and orange lines from before, which show the high expected skill LIM and IFS forecasts. That is the 15% of forecasts that had highest signal to noise ratio. What we see here is that when we filter the initial conditions to only include the stratosphere SST eigenmode variability, we recover nearly all of the high forecast skill that we had for the full initial conditions. However, when we only include variability that's associated with the internal variability eigenmodes of the LIM, that we find that forecast skill drops below 0.5 almost immediately beyond week 1. This highlights the fact that nearly all of the forecast skill that we're isolating for the high expected skill forecast are associated with those LIM eigenmodes that have a strong stratosphere and SST component to them. To summarize so far, we've been able to identify high-skill NAO forecasts ahead of time using the LIM signal-to-noise ratio, and we have shown that these skillful forecasts are associated with LIM eigenmodes that represent stratosphere SST-related processes. A natural follow-up question, however, is what do these modes actually look like? One way that stratospheric and tropical processes are thought to modulate NAO forecast skill is via downward propagating positive or negative northern annular mode anomalies. Here I'm showing 17 negative NAM events composited using JRA 55 between 1979 and 2017. The familiar dripping paint pattern is evident, whereby a large anomaly is first seen in the stratosphere, which is then followed by same sign anomalies that persist in the troposphere for anywhere from 30 to 50 days. In the following slides, we will show how the LIMS eigenmodes can be leveraged to understand the relative importance of purely stratospheric versus coupled stratospheric SST processes for driving NAM and NAO variability. Now, in contrast to our earlier NAO forecast results where we used the LIM eigenmodes to filter the forecast initial conditions, here we will filter the NAM time series itself. Of course, the LIM only has a limited set of variables and a limited set of vertical levels, so to overcome this, we created a ridge regression model that takes as input any time series of LIM state vector output or data projected onto the limb state vector and outputs NAM time series on vertical levels between 1 millibar and the surface. This enables us to filter the NAM into variance associated with internal variability, which, recall, was not predictable beyond forecast week 2, and variance that is associated with stratosphere and SST processes that was occasionally predictable out to forecast weeks 3 and 4. Okay, so this figure shows how the stratosphere SST eigenmodes and internal variability eigenmodes contribute to the total variance of the 17 observed negative NAM events. The leftmost panel shows the original unfiltered composite of 17 observed negative NAM events. The middle panel shows the stratosphere SST eigenmode contribution to the total composite, and the rightmost panel shows the internal variability eigenmode contribution to the total composite. Note that when added together, the middle and rightmost panels equal the original leftmost panel. This means that nearly all of the long-lived NAM anomaly is captured by the small set of more predictable stratosphere SST eigenmodes, whereas the internal variability eigenmodes only contribute to the total anomaly out to about day 10 at the surface and maybe out to day 20 or 25 near the tropopause. This is consistent with our earlier finding that nearly all of the high-skill NAO forecasts are associated with the stratosphere SST eigenmodes. Now, a natural question that one might ask is, what is the relative importance of tropical SST versus stratospheric processes to the strong NAM events? The problem with using the observed record, however, is that we only have 17 events, which is not enough to separate the contribution of SSTs from the stratosphere. To overcome this, we run the limb as a climate model for roughly 300,000 days, which allows us to consider over 3,000 NAM events. If you will recall, earlier in the talk I mentioned that the stratosphere SST eigenmode subspace consisted of one eigenmode that was primarily stratospheric in character and did not have any SST variance associated with it, and a set of modes with joint stratosphere SST components. So, moving forward, I will ignore the internal variability component of the NAM anomalies and instead show NAM anomalies split into components associated with the single stratospheric eigenmode and the joint stratosphere SST eigenmodes. Okay, so here, the leftmost panel shows the roughly 3,000 NAM events from the limb climate run. Recall that the NAM events are defined as periods when the NAM at 10 millibars is highly anomalous. Note also that the anomaly composite is so smooth, that is, it lacks the familiar dripping paint features in the troposphere, simply because we are compositing over 3,000 events. Indeed, smaller subsamples of the limb climate run also look drippy, similar to observations. What is striking is that nearly all of the downward propagating NAM anomaly seen on the left is associated with the single stratospheric eigenmode that has no SST component. That's the panel in the middle. Whereas the joint stratosphere SST modes are essentially irrelevant. That's the panel on the right. Now, does this mean that joint stratosphere SST variability is unimportant to NAM or NAO variability? The answer to that question is absolutely not. To see this, we constructed a second NAM composite, but instead of compositing on time periods when the 10 millibar NAM was anomalous, we composite on periods when the NAM at 300 millibars was anomalous. For these periods, we get a different NAM anomaly that has a stratospheric component but is primarily tropospheric in character. We see that in the middle panel, the downward propagating stratospheric eigenmode still contributes, however, its anomaly pattern terminates just above the tropopause. In contrast, the eigenmodes associated with joint stratosphere SST variability explain the bulk of the anomaly pattern. Now, what do these two types of NAM events look like in terms of their surface impact? To see this, we composited sea level pressure for the 40 days following event onset. For the stratospheric-based events seen in the top row, the sea level pressure anomaly has a primarily Atlantic signature, and as mentioned before, has zero SST anomaly that's seen on the far right. In contrast, the tropospheric-based NAM events, which are shown in the bottom row, have a more annular signature in terms of sea level pressure, with centers of action over both the Atlantic and Pacific basins. Interestingly, the SST anomaly that goes along with these types of events exhibits a non-canonical ENSO pattern. With that, I will put up my conclusions here for folks to read, and thank everyone for listening.